My name is Roman Samchuk. I'm an engineer and project manager at SDC Verifier company. And today we're going to talk about the crane safety, basically the lifetime prediction for lifting equipment with EN 13001 standard. So this is a short agenda. I'm going to spend just 1 or 2 minutes on introduction who we are. Maybe not all of you are aware of this. We'll smoothly move to what is EN 13001 standard itself. We'll talk about its background, need in use, etc. We will focus also on the FEA results and the use case examples, basically why we have that. Then we will move to the main topic, which is essential criteria for accurate fatigue analysis. We will talk about lifetime extension, reviewing some other industry standards for fatigue, and a short Q&A session at the end. So introduction, who we are. Basically, in general, we do two things. First of all, we provide comprehensive engineering consultancy services in different industries. So starting from civil engineering, heavy equipment, aerospace, offshore, and maritime. And the idea is that we do global verification of the structures for fatigue, for strength, global buckling. We do basically code checking according to standards. We do design check and optimization afterwards, certification support, tender support, and cloud-based engineering solutions. Besides that, we also develop our own software, which we use directly. So the background of this, okay, we are deeply involved into the engineering consultancy services, and we see that a lot of routine can be actually automated. So we came up with the software, and we are trying to make life easier also for other users. So what is EN 13001 standard itself? A short background. So before the EN 13001 was introduced, the industry actually followed different national standards and guidelines, such as, for example, DIN standard 15018 or old NEN standard, and of course the FEM 1.001 standard. So the main problem here on this screen is that these rules were developed in the early 80s and need to be updated to align with the latest knowledge and more efficient design tools being used. So many structures, they were produced a long time ago and typically designed according to FEM, specifying expected lifespan at the end. However, due to the use of manual calculations, the level of detail in the design was often low, right? So we were receiving the ballpark idea on the results, predicting, for example, okay, what is the service life for this part of structure or another one? And that's resulting in quite conservative assumptions, quite far from reality. So as a result, the condition of cranes can become uncertain over time, and basically both locally and globally. And at the end, it is crucial to perform proper maintenance and regular inspections to ensure a safe working environment and prevent costly equipment downtime. Because basically, if it's not done, the consequences, they are fairly dramatic, right? So we are starting with the small cracks, which are continuously growing. Very often they're found in the hidden areas. They continue to propagate and ending up with the big cracks that do not simply allow us anymore to continue the working conditions. So to avoid these problems and make the calculation approach more accurate, the need of revision of this FEM 1.001 occurred, especially to make it more harmonized, as is directly mentioned in the FEM standard itself. So here where we have EN 13001 itself, so mainly it consists of 3 parts for the crane structures. And when you dive into details of this standard, when comparing it with the other national and industry standards, it becomes clear that this is a new standard that employs unique approach to calculate both strength and fatigue of the cranes. So in addition, because of these reasons, and of course required level of detailization, which is fairly important for us, the finite element analysis approach becomes a must-have part in structural verification that provides a high level of result accuracy. So what I mean here, we call it simulation. On the left part, you can see the typical, well, in this case, this is a floating crane, but the idea is that FEA results represent a real behavior of the structure and helps you to study all internal forces. So starting from deflections, some maybe actual forces, shear stresses, and of course, fatigue-prone areas to prevent failure in the future. So couple of examples. How does it look? These are the typical projects we had chance to do. So in this case, you see how accurately basically the FEA results representation meets reality. So in the current case, this is at the tips of the stiffeners, or for example, the very local problem found here, where while the rest of the structure is in good condition, or another topic like this. Yeah, so these fatigue-prone areas very often are hardly reachable because basically they're coming down to the local stress concentrations. And of course, nobody wants to inspect whole structure because this is a time-consuming process and this is also a costly process. So on this example, this is a good example which shows that basically from visual inspection from the outside, that was impossible to see the crack which actually existed inside of the structure. So finite element analysis approach helped to identify it, and then when the inspection is done, basically because also another problem that there was no access, we found more than 30 centimeters, sorry, crack inside. Right, and of course it's applicable to all crane designs. And so we have wide experience in the crane calculations, starting from the simple unloaders, jeep cranes, STS cranes. So, well, basically all type of container cranes we have experienced. Also overhead cranes, of course, and also unloaders, stack reclaimers, straddle carriers, and so on and so on and so on. So going further and starting from a simple, what is fatigue itself? So fatigue refers to progressive and localized damage, right? That occurs when structure is subjected to repeated loading and unloading cycles over time. So crane is a very nice example actually to show that, because if we have trolley which is moving from one extreme position to another one, of course that creates a maximum and the minimum stresses, right? So the period of time when stress of the load varies from its minimum to maximum and back to minimum cycle, that we call one cycle. Yeah, and when the structure is subjected to cyclic loading, like in this example of this crane, stress level fluctuates, causing microscopic cracks. Sorry. So, for example, at the very local spots, these cracks to initiate and propagate within the material, and consequently, it can cause the failure of local elements or the global ones, depending on the results. So, yeah, basically the same result example here. So that's actually a phenomenon that leads to this failure. And if we're talking about the N13001 standard itself, let's start from something simple. Yeah, just a disclaimer, I will not mention every single detail in this standard because I'm a bit afraid that we will not simply fit into this time range of 1 hour, but I will try to focus on the most important things which make significant influence on the results. So in terms of the N13001 standard, we were talking about fatigue. Here you can see a simple execution of the proof example. So the idea is that the maximum range of the design stresses should not exceed the limit design stress range, which is this one. Yeah. Also, according to formula, we can already see what is crucial in the fatigue, because basically The limit design stress range consists of several things. So one is the characteristic fatigue strength, which is in short our notch classes or the weld quality. We have another factor here, which is fatigue strength specific resistance factor. We will stop on it in detail. And last but not least, this is a stress history parameter, which was additionally involved in EN 13001 revision compared to FEM standard, which basically applies a kappa factor approach. Right, so what is this stress history parameter? In short, it helps you to accumulate fatigue damage based on the applied number of load cycles and depending on the stress range. So here we see the stress range compared to the maximum one taken to the slope constant m power times the ratio between the relative number of load cycles to the total number of load cycles. So already from these formulas, we can end up with the short list of important things in fatigue according to EN 13001 standard. First of all, this is level of detailization. Although it's not mentioned directly in the standard, it is obvious that it is required to have to be able to find a fatigue-prone areas in the crane. So we cannot apply anymore our hand calculation approach if we want to get enough precise outcomes. Second thing is the stress range, right? That's what we were talking about. So the difference between maximum and the minimum stress, that is crucial. Next two things are quite dependent. So this is characteristic fatigue strength, which is coming down to our quality of the weld and the notch classes. I'll explain later on what is this. Fatigue strength specific resistance and the stress history I was talking about a few seconds ago. So I'm going to walk through one by one through these items and to highlight how to use these items, why they are important, and so on. First of all, level of detailization. So this is our modeling accuracy. On this screen, you can see typical example of the container crane, while all important connections are outlined separately. So what does it mean? You know that when the crane is subjected to the load, the idea is that our forces are transferred between the members through the connections, where you have a lot of welds. So basically, welds are the areas where, with the high probability, our cracks occur, right? And all these things, they should be modeled in detail when we're talking about finite element modeling approach. Why? On this screen, you see the typical example. So the first, the upper left picture is the situation when the crane is modeled with the simplified approach, so 1D elements. And here you see the ballpark idea on the fatigue results. So in general, it does not give a good representation on the fatigue-prone areas, especially because the simplified beam element approach gives us stresses only in one direction, while the complex designs involving the very local plates welded together, they are defining the complex notch classes to be applied there. So at the end, when you receive one result per whole cross section, which of course not enough for even for the easier visual inspection. So the difference here is that when you change it to the detailed shell modeling approach, it happens to be that all these high fatigue damage values, they're ending up to the very local problems. So it once more time proves that the simplified approach, either it's hand calculation or a simplified beam modeling approach, is not enough simply to say how much time is my crane left. Yeah, so because if you fix these local problems, there is, with the high probability, you can still extend this lifetime. Yeah, so you see a couple of spots already here indicated, and if you take a look to the details, you can directly see, okay, I have few spots with the stress at the stress concentration locations here. I can easily see them, and a couple of them are shown inside of the structure. So it's not that easy to see, because in very often you simply have no access to your structure. By the way, these plots are generated with our own software, so yeah, I will stop on it in detail, but all these nice pictures and the results are done with the help of it. So this is one more example. How should we care about the model? Yeah, in some cases you need to model a large part of the structure, not only connection. If we need to provide a high level of accuracy, including the gantry system, and of course it's not limited by the main steel structure, and we should care about the bolts as well. So in our situation, we model all the bolts as well, because one thing is that their strength level might not be enough, which potentially can lead to the failure. Another thing, fatigue also exists in the bolts. So that's about the detailization. The next thing I was talking about the loads and the real crane working condition. So having a crane, just a short background, if we have a trolley, it's picking up the load and putting it down somewhere, it's moving in that direction, then moving back. So basically it creates the vertical load. Our crane is able to travel, so it creates also some inertial forces from the crane, from the lifted load and so on. That these complex working conditions, at the end, they are ending up to the separate load influences. And these load influences, they are precisely described in this standard. So what you can see here, you have different load types, especially the ones I was talking about. So starting from your own crane mass of the hoist load, some inertial forces, which you should take into account. And in addition, you need to apply dynamic factors to all these loads. Yeah, so the background idea of the fatigue according to Ian is that we focus on the regular load situations, taking into account dynamic factors and neglecting our partial safety factors. But the question here is that, okay, we have this list of the loads which we should combine together times the dynamic factors, but we have different positions of the crane. So basically one load situation means that it should be multiplied by 13. So this is number of our trolley position to be able to pick up the accurate stress range along your boom and the girder and in other parts of the crane. So that's one thing. Then the crane moves in two directions as well as the trolley. So you should take into account different signs. And at the end, these simple load cases, load combinations A, become pretty extensive. And very often you can end up with more than 100 or 400 different load cases simply to check fatigue. Yeah, so it's regardless the strength checks. So of course we have a workaround for this because we use own software where you can simply copy all these load cases and simply paste it there, right? So directly in the window, or you can create them from scratch. However, when we're talking about these loads, what becomes crucial, I was explaining that, okay, if we have a vertical load, so my trolley lifting up the load with a certain mass, right? If it does it here, also here, so it creates a certain stress range, delta sigma. So the higher my load is, the higher my stress range is, of course. So which also means that the dynamic factor for the vertical load becomes crucial, right? And EN 13001 standard highlights all advantages of this dynamic factor calculation, for example, to old standard FEM, which is pretty conservative. So what it does here is, as soon as you start to lift up your load, you create a shock impact on your crane, and you can calculate it simply with this formula. And the magic of this formula compared to FEM standard is that you can play with this factor depending on different characteristics. So it's not only about the hoisting speed, but also about these parameters like a hoist drive class. So the hoist drive class allows us to basically, well, I will maybe mention this one at the end. So it allows us to focus also on the stiffness class of our crane. What does it mean? Having your typical crane design, which is your container crane, when you apply the load at the extreme position, you can measure your level of deflection, and basically depending on the level of this deflection or flexibility of your structure, you can end up with the different factors beta B, beta 2. Yeah, so it's varying from 0.17 to 0.68. So already you can make your design or influence on the fatigue better with the stiffer structure. That's one thing. And another thing, you can make a proper selection of your hoist drive class. Yeah, so depending on its conditions, so whether it's a stepless hoist drive control, which performs continuously increasing speed, or it automatically ensures that your dynamic factor does not exceed a certain value, you're ending up with fairly different values. Yeah, so they're varying from 1.2 and ending up with 1.05, for example. So you see the influence is huge, and EN 13001 suggests a good tips and tricks how to make your design better. Of course, it's not limited by the dynamic factors. All other loads, they matter as well, and sometimes the values according to specs, they do not simply meet our reality, and it was to do measurements and inspection on these things. For example, on the accelerations and velocities, so that you can measure them precisely and make your calculation approach more realistic. And this is also applicable, by the way, to the dynamic factor. So another thing about the load spectrum itself is that, okay, if we have a crane, in old times, there was an assumption that we need to come up with a certain design load spectrum class. Yeah, so this is example taken from NAN standard, for example, but the idea in FEM is the same. So originally at the design stage, we make assumption how much is my crane loaded most of time. And in very often, this assumption was very conservative, supposing that the crane is all the time working with the maximum load capacity, which is of course not true. So even if you have a grab, for example, instead of the container, it's not always the case that your grab is full, right? So it can be, for example, 70 or 80% loaded. The same thing with the container. You have different size of the container, different content, and so on and so on. So you are not all the time picking up and putting down containers with the same weight. And it happens to be that often our cranes are picking up the weight, which is only 75 or 80%, for example, of the total load, which makes a crucial influence on the real load situation. Because according to the initial crane design, we see that our service lifetime is close to the limit already. However, the real situation is different because we were simply not loading this crane that much as it was designed at the very beginning. Okay, another important thing I was mentioning is the characteristic strength defined by the notch class. I took, two pictures just to easy represent what's the difference and what it's coming down to. So when we're talking about the welding quality, which is regulated by the ISO standard, there are different qualities prescribed by the EN 13001. So this is from B start, quality B, C, and also quality D. So depending how good is your welding quality, you can extend or reduce your fatigue lifetime, right? So the better your quality is, the better, the longer your lifetime is. So how does it look in a standard? Besides the welding qualities themselves, you're ending up also with the different strength depending on the connection type. So for example, along the weld, when we want to consider our fatigue strength, we should always take into account 130 for the lower weld class or 180 for the higher, unless we have an intermittent weld type. And for example, for this type of connections, you see this is significantly lower, and this is varying from 90, 80, 71, and so on. So that gives you a lot of space to play with your design. So if you want to extend your lifetime, for example, at the design stage, please choose the right the right option. And the typical example here is that, yeah, on the left side, you see the top pylon head connection from the container cranes verified with SDC Verifier, and you see that it happens to be that fatigue-prone areas are found at the local stress concentration locations. So here, here, and here. And the drawback is that, well, first of all, because there is simply a stress concentration which sometimes is hard to prevent. However, in this case, you see on the right side several options, right? So depending on the radius, which should be at least 50 millimeters, and an angle, you're ending up with the different values. Same as for here. So, for example, if it does not meet the basic requirements and this radius is less, you see you have -2 notch classes, which is already not even 71, but you're ending up to above 50, right? So this is a huge reduction, and these tips, this is a good indication what is supposed to be done and what you can still do. So, but then the question is, okay, we have a lot of welds and we have this complex finite element modeling, how to basically define all these welds, because it happens to be quite time consuming. So we developed a standard solution in SDC Verifier. We have an automatic recognition of the welds. So this is a typical example. Basically, this is part of the boom of the crane. And the only thing you have to do is to run weld finder tool, click one button, and then your all welds gonna be recognized. And even if you have a really simplified modeling approach, you'll get a notification where you only need to give an idea to the software which part is welded and which one is not. That's it. So you don't have even to remodel the things. So at the end, it automatically recognizes all the welds in your model. In a second, you have the full list with the coordinates, also with additional settings for weld strength check verification, and you see you have already identified which part is welded and which part is not welded. So you don't even have to guess. So at the end, when you do highlight, how does it look in the model? It looks like this. So all the welds are automatically detected. Of course, it does something more for you because the background idea of the stresses for fatigue is more complex when it comes to the finite element modeling approach. So by default, you receive stresses related to the local element coordinate system, which sometimes can be quite chaotic, right? So you could get things messed up. But the idea is that when you do fatigue verification, all the stresses should be oriented into the weld direction. So this process is also automated by the software just to avoid a lot of routine. And the idea is that we have stresses along the weld, perpendicular to the weld, and for shear. And what's moreover, it recognizes also intersections between the weld, which are, by the way, the weakest point. Because what happens here, if you have connection like this, and basically this is a base material, so this material is a non-welded part for the welds, and any plate which is welded perpendicularly or additionally to this plate is considered to be welded, and thick strength of this part is of course less. However, if you have another plate welded perpendicularly to this part, you have already an intersection of two welds. And whatever direction you're looking at becomes a perpendicular to the weld direction. So depending on from which side you're looking on the thing. So basically at the end, these all crossing welds, they are fairly important and they are very often a fatigue prone areas. So of course, we can set up exceptions because you might say, okay, I have rolled sections and not the welded one, how to deal with them. So that's also coverable with the software, what you can see on this screen. And at the end, when you do complex recognition, you can also automatically set up all these complex numbers just with few clicks. So in addition to the recognized welds, you are receiving the nice picture which shows you, okay, all these welds colored in blue, they are having the notch class of 100. Here I have weld intersections, and non-welded area, which is colored in orange, is having the higher notch class, and so on and so on. Right, so it allows us to focus on the real problems and to make sure that these values are representable according to this real situation. The results accuracy is also amazing. So at the end, what you get is, of course, the fatigue damage for the non-welded part is less. So most likely it's within the limit, while all the welds are representing the higher fatigue damage. And especially at the weld intersection locations, we have locally high fatigue damage, which we should deal somehow with. Yeah, that's why, by the way, you have all these red holes in a typical. So if you have a girder like this and you have a cross section of it, you have an internal section here. So all these red holes are done to avoid these crossing welds, especially because of fatigue. Next thing, which is not less important, this is the real crane usage. What do I mean is, I was mentioning a couple of times that the trolley is traveling from one side to another one. However, how often does it do this thing? From one extreme position to another one. What do I mean? So depending on the size of the ship, we have different positions of the trolley. Sorry, maybe very nice. Let it be like this. Yeah, so depending on these things, you are using different trolley positions. And based on experience, a lot of cranes are rarely using this extreme position. It does not mean basically that they are not used at all. Of course they are. But if it's rarely used, it means that we should not take them into account 100% for the fatigue verification. So what we should do, we should split our trolley position usage into the different ones and make a ratio between the number of load cycles. So what do I mean here? We see that the position number 3, from position number 1 to position number 3, we're using only 9%, 5% in our case, which can vary to 10 or maybe even 15. So we put it in one load group and we say, okay, all the stress ranges calculated within this range should be summarized as many times as specified in our number of load cycles, which is only 48,000 of load cycles. This one becomes around 40%, this one 70, and we see that most of the trolley positions are used here. So basically from position number 5 to the land side legs. So that's where the real influence is coming from. And that also means that we are involving the lower stress range, because we all know that these extreme trolley positions are crucial when they are directly used for the stress range calculation. Of course, the same thing is applicable to other type of cranes, like on this example for RSC cranes, where we have different lanes here, right? And depending on the trolley positions, we're ending up with the different percentage ratio. It's also related to the jeep cranes like this, because you have different positions as well. So you have extreme back position and the front position, and it happens to be that, for example, second position is already 30%, while the first one is only 10% and the first one 50%. Yeah, so you can play with these things directly. Next thing I was mentioning at the very beginning is the fatigue strength specific resistance. So the fatigue strength specific resistance factor is used to account for uncertainty of fatigue strength values and possible consequences of fatigue damage. Yeah, so the factor may be specified individually for each detail. And in short, it means that for structural parts that even comply with fatigue verification, but where the detail is not easily accessible, you see, so basically these rows, for inspection, the additional safety factors are popping up. And it depends on the hazard risk for persons and its accessibility. So in short, if your detail is simply non-accessible. You cannot get in, and it creates a significant hazard for persons. Basically, you need 25% reduce your strength. Yeah, and this is 15 strength, even if it's without hazard per person. So basically, the idea is that this additional safety is related to the accessibility of your structure. The logical question appears, okay, we have all these things, we went through this, but how to avoid it? Yeah, so can we extend our fatigue lifetime somehow? The answer is yes. I mentioned at the very beginning that if we find the fatigue-prone areas, yeah, we should deal with them somehow, and we can reduce the further impact on these local areas, for example, with the help of the reasonable reinforcements. Yeah, so it tends to be that, okay, the crane owner think, I got a certain crack, I will simply weld it, or I will come up with the local improvements when it's continuing to grow. But these local solutions without calculations sometimes lead to the additional cracks repeated in the surrounding area and additional ones. Yeah, so the finite element calculations are the must-have on the list for these things. So what we do here when the fatigue verification is done, the detailed one, we do the complete inspection plan to compare the real crane state with the results identified. And basically, the experience shows that the results representation is fairly accurate, like it's shown on the right side with this simple example. Yeah, and how to deal with this? Well, a nice example is shown here for one of the overhead cranes. It turned out to be that the connection between the seal beam and the bridge, we've got the locally high fatigue damage level, and with the help of the local reinforcements shown around here, we've managed to avoid that and extend fatigue lifetime for the next certain amount of years. Yeah, so of course you can do a global optimization when a simple local, local additional reinforcements are not enough, but the idea is that avoiding these things and extending our lifetime is of course possible. So summarizing all the things, AN 13001 is the best option on the market, and it provides a very specific approach with the limit state method. So in addition to this, FEA calculations are required for precise results, or we should execute them based on a detailed modeling approach. And the essential criteria here, I would like to highlight first of all, FEA verification itself, stress range, and the background idea of the stress range. First of all, our loads, which are sometimes conservative, our dynamic impact, which you should carefully calculate, and our real load spectrum, so basically the crane usage. The next thing is, of course, the quality of the weld, our notch classes. If it's not set up properly, you're simply overlooking these areas and receiving the wrong results. That's a short conclusion. If you're ending up your welds with the poor quality, so it's not grinded down, or you don't have smooth transition, you involve this extra notch effect, which is a significant influencer in fatigue. Next thing is about accessibility of our parts, which involves additional safety, so according to standard, so whether your part is accessible or not, and of course at the end, stress history parameter depending on number of load cycles and positions on our design. Yeah, so besides the AN 13001, of course, there are multiple standards on the market you could use instead. So starting from Eurocode, for example, ending up with DIN VGL standard, or maybe even the same DIN 15018 with the Neurovision FKM standard, right? So multiple standards exist, and we have them all in the database. But in addition, I would like to highlight how do we deal with this at SDC. So, okay, we have a nice software, but what does it do? Here you have a typical workflow, and the idea of this workflow is that, okay, as soon as your model is built, it's read out automatically by the software, and all the parameters and the properties you have in a model are automatically extracted to the software. And then with the help of the pre-processing tool of SDC Verifier, you're able to apply multiple load cases. You shouldn't do that manually. You do recognition of your welds and the structural components, and then you do verification according to EN 13001 standard automatically. So all these complex formulas, you shouldn't basically care of them anymore if your input data is properly selected. And at the end, all these extensive results can be automatically reported, and if they are not allowable, you can always optimize that. And the main advantage is that you could say, okay, I have multiple changes. Why the hell should I do that each time? The answer is simple. If you select that once, and then you do any changes, the only thing you have to do is to synchronize your model, and all the steps are repeated automatically. And that's why you have these arrows around. Yeah, so that's how it looks in detail. So you create it once, you simply run them, all these load combinations. I was talking about them before, but that's the idea. You created them, then you have a separate window where you can carefully set up the different number of load cycles for the different positions of your trolley or the different load situation, right? So at the end, these things are summed up with the total number of load cycles. You recognize your welds automatically, and the only thing you have to do is to create your standard and set up few parameters we were talking about. So specific resistance factor, just to make sure that accessibility is allowed or not, right? The notch classes, which are done also automatically, I showed that, but you need to basically fill in values for the welded and the non-welded parts, because it can be, so we'll have this option open, because it can be that, for example, you did modifications or you would like to treat it differently because you simply do not agree with the end, so that this is also customizable. And that's basically it. So these things are also simple. So slope constant, you have only two options, and then at the end you get a nice results accuracy, which can be documented in the extensive reporting, which can be exported to the PDF, PowerPoint, or Word documents, starting from the very detailed description of your model, your calculation setup, how did I come up with my cycles, and ending up with your results showing potential problems and the improvements to your client, or share with your colleagues, of course. Yeah, so we have a wide range of customers around the world, so I will not stop on it in detail, and we have 15 minutes left, so I propose to go to the Q&A session just to be able to cover your specific points directly. Thanks for attention, and
Yeah,
that's it from my side.
You could write your questions in a chat or Q&A session, Q&A box from the WebEx. And Roman, thanks for the presentation. I have two questions.
By the way, it can be that we all understand that you have very specific engineering issues which somehow should be solved. So if you have doubts or you don't know how to precisely do that, we have enough of experience, so you can write to us and we can make a call and help you basically to assist with them. Okay, Petro, you said
yeah.
I
have a few questions here in a Q&A section. First is what notch class must be selected for the poor quality welds?
Okay, that's a good question. So depending on the quality, depending on the quality and the current state of your welds, standard prescribes in general several different levels. So this is C, B, and D. If you have a really poor quality, you can end up with D, for example, but in most cases, weld quality C is a good assumption for detailed verification. Yeah, but then keep in mind that you need to take into account different types of your connections besides the weld quality. Okay.
Yeah, there are another one. Regarding notch classification, not directly related to SDC, EN 13001 notches are for nominal stress. Unfortunately, EN 13001 doesn't offer DCs for structural stress, which is what we get when modeling with shells. Design checks should therefore still be quite conservative, right? Yeah, Eurocode 3 Part 9, for example, has separate DC for structure stresses, DC 90 to 112. I don't know those questions. And another one question is, are you translating the FAA hotspots to EN 13001 fatigue class?
Yeah, these are two very good questions. First of all, about conservativity. EN 13001 is based on the nominal stress approach. Yeah, so it is directly mentioned in the standard. So, okay, if you have a very detailed finite element approach applied, for example, when you have modeling with shells and so on, some of your results may be conservative. It is directly mentioned in EN. It is mostly caused by the stress concentrations in our model. As you know, when you do fatigue verifications, besides the quality of your welds, you're dealing with the stress concentrations. So basically, when you do a detailed shell modeling approach, then you do not have to take into account the stress concentrations additionally because they are already taken into account in your model. So in this example, you can see, okay, if I have the very strict transition like this, right? So basically, I have connection at the right angle. This is apparently a stress concentration point. So in your model already, if you do the general stress analysis, already is gonna show a relatively higher stress level here. Yeah, so basically, it tends to take into account the stress concentrations, which are very often mentioned with the factors in multiple standards. So when you do this, it's fairly enough, and based on the experience, it shows very representative results when you do a shell modeling, basically, which takes into account with the modeling approach the stress concentration, and then you take into account appropriate classifications, so notch classes. Yeah, even if it can be that, okay, I have the slightly conservative, maybe relatively more conservative outcome here compared to the real situation, that's a still a tension point. You should never neglect that. So our suggestion is this approach replaces stress concentration factors because you simply pick them up with a model, and then if you do apply accurate classifications, then that's a pretty much accurate situation. That's one thing about the hotspot stress method. That's a good point. Although most of engineers, they simply use a general approach like, for example, if I have the shell model with nodes like this, yeah, so they simply extract elemental stresses from the intersected elements, which is pretty much okay because basically, if you put the thickness on, you see that if you extract that, let's say, half at the distance of half of your plate thickness of an element, then it's still a good representation. However, here at SDC, we have separately implemented a hotspot stress method. And the idea is that, okay, if I have the weld like this, and you have the mesh, certain mesh size, because the stresses are also highly dependent whether you have a coarse mesh, so basically your element size like this, or you have a fine mesh so that you have detailed results. We implemented this according to IIW standard, and the idea is that you're able to extract stresses at a certain distance, right? And then to interpolate these stresses into the weld. So basically, the hotspot stress method is also applicable to EN 13001, and I would say most of the standards allow this method as a very good, precise alternative to the standard approach. Okay, more questions?
Yeah, the one more question. I don't know if you have time to answer. It's about how you model and how would you model and select the notch class for the cover plates covering the stress relief hole welded on top of the pipe to gusset connections. If you don't have time, we could answer it email or something like that, or you could answer now.
Well, basically I do, but could you repeat it again? Because there was a quite extensive description.
How
So
would
there was
you
a gusset
model
plate.
and select the notch class for cover plates covering the stress relief hole welded on the top of pipe to gusset connection?
Well, basically, I can answer maybe in more general thing, just to avoid any let's say distinctions between the modeling approach asked in a question and what I'm gonna come up now. But the idea is that if you have an overlapping connection, like okay, I have a pipe. Sorry. Oof. Yeah, I have a certain gusset plate. Sorry, can be done like this. Yeah, so that's probably what was asked. And here you have some covering plate. That was the question. I don't know who asked that, but that's how I just imagined this. So if you have the pipe like this, maybe that's not the perfect drawing, and here you have a gusset plate. Sometimes they do a basically an extra plate which provides stress relief at the ends of this. Well, basically for this stress concentration location. And that also often used as a reinforcement. So the idea is that if you have this kind of connection, you have to model that in detail as well. If you do a shell element approach, if I have a cross section like this, if I do a shell element approach, basically this is how it's gonna look like. And this small plate is located at a certain distance, right? So you should take this effect into account. And then basically what you can do, you can simulate your weld used for this pipe with a separate row of elements. And then when it's done, you can set up the appropriate notch class directly to these welds, because apparently this is a welded part, and this extra row of elements will simulate your weld. Well, this part basically is gonna be a non-welded part of the structure. So again, you see, your question is a very good one, because BIM modeling approach and any simplifications would not allow to pick this effect and to take that into account. So with this approach and the detailed classification, you can do that.
I think it's good to see the model, and maybe we can follow up afterwards and show a detailed demonstration of this. Thanks.
By the way, if you have the real situations you experienced in your projects and you're struggling, you can always write an email to us, and I will be happy to assist you with this. Okay, more questions?
No, there are no more questions. I think we have a great time in this presentation.
It's 10:04, but one last sentence is, I did not, of course, mention all possible factors, all the complicated formulas, procedures, and so on, simply because we don't have enough of time for this. I was focusing on the most important things, but my message is that if you use appropriate software for these algorithms, then you're also on the safe side, because you see there are so many details, then it's easy to mess up with this and basically to get confused, and at the end be on a very pessimistic side in terms of your crane lifetime, remaining crane lifetime.
What should user define in SDC to make the verification automatic?
Well, basically, just a second. I had this. Basically, this window I showed, that's a nice indication what you select. So in general, what you have to do is to recognize the welds. Yeah, so just, well, 99% cases, you don't have to do any changes afterwards as soon as your welds are recognized, but this is also customizable. You might say, okay, I want to have additional weld somewhere here because somebody damaged that and I have it simply there. And at the end, you need to properly give an input to the software with this. This is a wizard window from the standard you create. So here you have an option also for static strand. You can play with the methods you would like to focus. So either it's limit state method or allowable. I want also to say that limit state method, that's a good replacement instead of a FEM standard, which is based on allowable stress design. And for what is related to fatigue is basically here. There it's summarized. In fact, the most important thing is that your accessibility to the plate and the notch class. And these things are fairly typical. Yeah, so this one is not used because you can avoid it because this is based on a simple approach. If you do the detailed one, this, the stress history is calculated automatically, and you should focus on the notch class and the accessibility of your details. Okay, I hope that answers.
Yeah, thanks. There are another questions about notch classes. The setup of notch classes looks like quite complicated, especially in the finite element model. How does SDC Verifier deal with this?
Pretty simple. Just a second. We had the notch classes over here. So what I showed a while ago is that we have an automatic recognition. What software does in this case is that it recognizes all these welds, but then they are classified separately. They're classified separately into the welded and non-welded parts. So basically this nice picture which you showed on the crane where you had different values prescribed to the standard, that was also done automatically. The only thing you have to do is to make sure in numbers. So depending on the category and the welding quality, you're ending up with the different numbers. And of course, software cannot automatically recognize quality of your weld because it's simply impossible. Yeah, that's something related to your crane state. That's it.
I don't see any questions in the chat or Q&A box. Maybe if you want to ask by the voice, you can unmute yourself and ask it.
Hi, hello. I don't know if you are hearing me.
Yeah, hello. I do
So,
hear you well.
yeah, so my name is Ricard Sobral. I'm from PSA Cines, and I do have a question. All
Okay.
the shared analysis from the modeling software, all of that only can be done if we have the equipment manufacturer design calculations, right? Without those calculations provided from the manufacturer, will not be possible to do all that modeling and all of that analysis. Is that my question?
Well, actually, not really. The initial calculations at the design stage, that's something else because at the end it gives you the service lifetime for your crane, the lifespan, right? So this is an indication that your crane design is good enough for a certain amount of years. However, with this approach, we do another way around. So we are recalculating your crane with the real situation because very often at the initial stage, these design assumptions were very conservative, right? So we do the opposite way. We are trying to prove that under the real crane working conditions and the real loads, the actual lifetime is not that bad. So basically, it can have problems coming down to the local spots, but that's it.
So in order to do it, what data you would require from the existing grains?
Yeah, that's a good question. Basically, we need only the typical input data according to specs. So what are the speeds, accelerations? What are the weights of the crane? Yeah, because weights determine COG of your crane, which create a different distribution on your stress level. We also need to know the pattern of usage of your crane. So for example, if you have a basic input, what is the typical ship size do I have so that I could identify what are the trolley positions normally used? That's good enough. Because in this case, I can come up with the typical pattern of the trolley movements and then avoid this conservativity with the extreme positions.
But
So in short, if we have a typical input data according to specs and the idea on the trolley usage, that's enough to allow that.
okay, but I have another question. Not having this data from all these calculations from the equipment manufacturer and putting all the data that you mentioned on the model, how the model knows where is the real weldings on the equipment in order to understand whether it is a weakness or it is a strong point. Because not having the drawings, all the manufacturer data, the model could interpret weldings in a place that there are no weldings on that place, or is not that possible to happen?
As long as your welds are shown on a drawing, they're well represented by the FEA model. So the answer is simple, it's done by our software. And wait a second, I will try to draw it.
No, but my question is, could the model assume weldings where on the real crane does not exist because the crane manufacturer does not put any weld on that place?
Exactly. It can, because we can tell to the software to do that. So that's what I meant. So most of the things, they're automatically recognized if it exists. If something does not exist because manufacturer forgot to put that, but we know that it's there, we can add it manually. I can say to the software, please take this additional weld into account, which is over here, and it will be accounted for.
Okay, so in order to have the real modeling of the existing crane, you require the data, but also you need to visit the equipment to take your own visibility about where is the things, right?
Well, normally, based on our experience, I would say that this is rather exceptional case. So normally, if you have drawings and they specify that this is welded in that way and that's in this way, it meets reality. Of course, there might be distinctions which, because we're all humans, maybe someone did something wrong. But at the end, this spot will pop up, right? Because we still pick up a real stress distribution over the surface. So if there are certain uncertainties, you still will notice relatively higher stress level at that spot than now. So that's already an indication that, okay, better to inspect this spot as well. But in general, you can do it in 2 steps. First one, you do everything according to drawings, yeah, because we engineers, at the end, we believe these drawings, if, well, unless anything else is mentioned. And then if we see that the situation is more than acceptable, most likely you will not have serious problems at this local spot, which your manufacturer forgot to mention, which is the very small plate. But in general, we can still keep tracking this situation, because the general approach is that as soon as you get first results, you do visual inspection based on them, and then at this moment you're able to see whether your FEM model meets your reality and whether your results are meeting the real crane state.
Thanks, Roman. There are the last question, I think, and I could answer.
Sorry, Pedro. Ricardo, did I answer your question with this?
Yes, yes. So I would
Okay,
like
good.
to finish just saying that so we can use your capabilities in two stage. On the design stage in order to check whether the calculations being provided by the manufacturer, what will be the weakness points if there are any weakness points on their design. And also during the operation of the existing crane to understand whether we will have any not visible or any hidden cracks in somewhere that are not accessible for the normal inspection.
Exactly. And the second option you mentioned is fairly dramatic in, well, very often, because a lot of cranes were manufactured simply, I don't know, in 80s, maybe even 70s or 90s. And, you know, the quite simplified approach was applied to them. So it becomes even more important.
Thank you very much.
Patrick,
as I said, there are last question that I saw, and I could answer it by myself. It's about is this presentation will be available and how to get about new webinars in the future. Yes, its webinar is recorded and we will upload it on our YouTube channel and send to all who were registered to this webinar and attend it. And we suggesting you to subscribe to our YouTube channel and follow us on LinkedIn, and new webinars we announce on our website and social media, and we will include you to our mailing list, and we'll send if something new will come in a near future. So, and also this recording of this webinar, I thought I could do it maybe tomorrow or on Monday, but yeah.
Okay. Petro, are there maybe more questions? Because I think I saw one popping up.
Maybe it's someone write direct to you Q&A, because in a public Q&A or in my Q&A I didn't. So
okay. I saw some notification, probably it was from team, but if it's the case, please, gentlemen, unmute yourself and you can ask it directly because it's easier.
In fact, I sent the same question to you directly at first, then I shared on everyone. You already answered the question.
Ah, okay, good.
Thank you.
Okay.
Thanks a lot for all who attended this webinar. Yeah.
Okay. Perfect. Again, if I did not cover some specific details which you were interested in or experienced in your own projects, you can you can reach me out by email, and then we can arrange a call and then focus on them, and then we will try to assist you with them. Okay, thanks for attention today. That's it. Good luck with your with the engineering.
Thank you.
Yeah, bye-bye.
Thank you. Bye.